Imagine walking up a staircase where every single step is exactly the same height. You never have to guess where your foot will land because the rhythm is perfectly predictable. In mathematics, a sequence of numbers that follows this exact kind of uniform, predictable rhythm is called an arithmetic progression. Looking at this two-dimensional staircase, we can see the sequence counting up: 4, 7, 10, 13. To navigate this algebraically, we need to map two specific traits. First is our starting point. We label the very first term as U1, which in this case is exactly 4. The second trait is the precise gap between each step, known as the common difference, represented by the letter D. We find this by taking any term and subtracting the term immediately before it. So 7 minus 4 gives us a positive common difference of 3. Sequences can also walk downward, and they can extend infinitely. In this new descending staircase, the terms drop from 20 to 16. Subtracting the first term from the second gives us 16 minus 20. The common difference here is -4. Before you can predict future numbers or solve any complex sequence problem, identifying your U1 starting point and your common difference D is the mandatory first step. Those two values are the engine of the entire sequence. Counting step by step works fine for small sequences, but if an exam asks you to find the 100th term, manually adding the common difference 99 times on your fingers will consume your entire test period. This is where we use the nth term formula shown here. To find any specific term, UN, we take our first term and we add the common difference multiplied by n-1. We use n-1 because you are already standing on the first step. To reach step 100, you only need to take 99 actual jumps. Returning to our first sequence, let's find the 100th term. We substitute our known values. U1 becomes 4, n becomes 100, and d becomes 3. 100 minus 1 is 99. Multiply that by 3 to get 297. Add the original 4, and we arrive precisely at 301. A quick warning here. When dealing with descending sequences, students frequently calculate the negative common difference correctly, but then accidentally drop the negative sign when multiplying it into the formula. Always carry the negative sign into the brackets. This formula replaces manual counting with instant algebraic scale. You can jump directly to any term in an infinite timeline with complete precision. Once you know how to find a future term, examiners will flip the logic. They will give you the final value of a term deep in the sequence and demand that you figure out its exact physical position. Look closely at this equation. We know the final value of the term is 301. What we do not know is n, the position of that term. The most common mistake here is plugging the total value into the n slot instead of the un slot. To find the position, we set the equation equal to 301 and work backward to isolate n. First, subtract 4 from both sides to get 297. Next, divide both sides by 3, leaving 99. Finally, add 1 to both sides. The sequence hits 301 exactly at the 100th position. Success in these exams requires treating every formula as a reversible equation. On a high-level exam, the goal is often to manipulate these variables left or right until the missing piece is isolated. So far, we have been looking at individual terms separated by commas. But if we replace those commas with plus signs and add all the terms together, an arithmetic sequence transforms into an arithmetic series. Series simply stands for sum. The logic of the summation formula relies on the fact that if you pair the first and last terms of an arithmetic sequence, their sum is the same as the second and second to last terms. Since we have n over 2 of these identical pairs, we use the primary summation formula shown here. We substitute 10 for n, 4 for U1, and 3 for our common difference D. Pause here for a moment and run the algebra yourself. Simplify the brackets first. 2 times 4 is 8, 9 times 3 is 27, 8 plus 27 is 35. Multiply 35 by 5, and you verify that the total sum of those first 10 terms is exactly 175. Your formula booklet also provides this alternative, much shorter summation equation, but notice the required variables. To use this shortcut, you must already know UN, the exact numerical value of the final term in your series. Choosing which formula to use isn't a guessing game. It is a strict audit of your data. If the question gives you the final destination term, use the shortcut. If the final term is a mystery, rely on the primary formula. Once you are comfortable calculating sums, prepare for a technical challenge. Exam writers will often give you the final sum up front and ask you to find how many terms it took to get there. As this visual shows, solving for an unknown n inside the primary sum formula forces you to create and solve a quadratic equation. Let's review the foundational rules. Sequences list the numbers. Series add them together. Always track your negative signs on descending sequences, and carefully separate the physical position from its actual numeric value. Mastering arithmetic progressions comes down to looking at this core set of rules. Define your starting term. Define your common difference. Once you lock in those initial conditions, you can trust the algebra to build the rest of the staircase.